Okay, so this lesson is really just another rehashing of the shortcut, quote unquote, of how to find the integral or the area underneath any curve. If you recall yesterday or during class today, we looked at the pattern that we saw that when you go from the actual function to the derivative. And so by using that very pattern, we can see that we can go from the derivative even to the actual function. We can work backwards, so to speak. So if I was to have 7x to the 6th, we would notice that what happens to this is the 6th goes up a power, so it becomes x to the 7th. And we, in essence, divide by that new exponent. And so that becomes x to the 7th. 3x squared becomes x cubed. And we would divide that 3 by the 3, and we would get 1 there. 4x cubed becomes x to the 4th. X cubed. Very similarly, remember what we're doing. Each time we're adding a power, so it becomes x to the 4th, just like the one above it. But when you divide by 4, since there isn't a 4 in front of it, it becomes 1/4 x to the 4th. The next one would become x cubed, but again, there isn't something in front of it. It's just a 1, so it's 1/3 x cubed. The next would become 1/2 x squared. The next one here, and let me just scroll down so we can see the rest of these, x squared would become x cubed, and again, that would be 5/3 x cubed. The next would become x squared, and as you'd expect, the 2's would divide out. Then we would have 2x squared. And the next would be 7x. Good, the x here technically is x to the 0, so when it goes up a power, it goes to 1. In the same way, we have negative 3x. So a constant gets the x value. Now think of that in the opposite order. If I was to do the derivative of any one of these that are written in brown and find its derivative, we should get what is written to the left of that in black. So in general, if f of x equals x to the n, then the derivative, if you remember, was you drop that exponent in front and we go down a power. Well, so then in contrast, if I'm going from the derivative to the actual function, what happens is we add 1 to the power, and instead of just dropping it in front, we would divide by that new exponent. So sometimes you'll see it like that, by the way, and sometimes you'll see it where it's written in that form. Both mean exactly the same thing. And this is, in fact, the fundamental. Yes, I couldn't have said it better myself. Fundamental theorem of calculus is basically looking at that very thing, and that is this right down here is the fundamental theorem of calculus. Well, how did we get there? Well, this is what you're looking at. The average rate of change, if you recall, is f of b minus f of a over b minus a. It's your slope. It's what you've known it to be. It is also the same thing, if you remember, as doing the average value of the derivative. If we did the area underneath the derivative and then divide by the length of the interval, we would get the same thing. Well, now look at this, okay? Now try and see if you can follow from this second step here to this one we've circled. If you look at it, they're both divided by the b minus a there. Hopefully you can kind of see that. In fact, that's really what we're saying. If I could almost eliminate this denominator from both of these since they're the same and look solely on the numerators, you can see that we have the integral from a to b of f prime of x, as you see here, is the same thing as f of b minus f of a. Another way that you'll see that written is you'll see f of x, and this line kind of means evaluating it from a to b, and that all means the same thing. And those, all three, are exactly. Let's do some examples of that. All right, so how does this become applied? How does the fundamental theorem of calculus apply here? So the first thing we would do is we would find the function that this integral represents. And so we would actually go up a power, so this becomes x to the 5th, and yes, we would divide by the new exponent. So that's 1/5 x to the 5th. And it's asking me to evaluate from -1 to 3. So what we would do then, what that basically is saying is we're going to do f of b, or f of 3, minus f of -1. So I'm going to do 1/5. You're going to notice I'm going to do something a little different than what you might expect. I'm going to put that 1/5 on the outside. I'm going to do 3 to the 5th minus negative 1 to the 5th. And so 3 to the 5th is 243, I believe, minus a negative 1, which makes that plus 1, so 244 divided by 5. And that's sufficient. Let's do another one. The next one would be 1/3 x cubed. We're going to do its integral. Remember, we're going up a power, divide by the new exponent. The next one would be 5/2 x squared plus 4x. Evaluated from negative 1 to 2. So now we're going to plug those in. So once again, I want you to see how I would substitute this in. That is 2 cubed minus a negative 1 cubed. Then we have a minus 5/2. And we would have 2 squared minus a negative 1 squared. Now this might seem silly that I'm approaching it in this way. And some of you might think, wouldn't it be easier if I just plug 2 into the whole thing and then negative 1 into the whole thing? I'll just tell you that the dilemma that becomes, real evident is that you're having to deal with fractions throughout the whole thing and getting common denominators to the whole thing instead of just grouping them together. I just would highly encourage you to do it in this format. It'll save you tons of time. So I have 1/3. I have 8 minus a negative 1, or rather 8 plus 1, so that's 9. I have minus 5/2. And this I have 4 minus 1, so that's 3, plus 4 times, again, 3. So we have 3 plus 12 would give me the 15, and then I have minus 15/2. So that would be 30/2 minus 15/2, which gives you 15/2. If you don't follow that, that's just a matter of getting a common denominator and finalizing that. Now looking at this next one, it looks quite cumbersome, and it truthfully could be, but what would be your first gut reaction to this? We haven't done anything with fractions or anything where we separate these or anything like that. Do you have any thoughts about this? My hope is that you look at that x squared minus 5x minus 6 and think, I wonder if I could factor that. Because that should be our goal. When we see fractions, we should factor them first. Do you remember that from last year? Factor fractions first. First, factor fractions. When you see a fraction, factor it first. If it's possible, factor it first. So let's see, can I? X and X, 6 and 1. Oh, different signs, bigger ones, negative. And what do you know? The x minus 6 actually divides out. This really is exactly the same question as the integral from 0 to 1 of x plus 1 dx. Again, this works out much nicer if you simplify that first. So you'd have that 1/2 x squared plus x evaluated from 0 to 1. So that's 1/2. We'd have 1 squared minus 0 squared plus 1 minus 0. So that would be 1/2 times 1 plus 1. So I have 1/2 plus 1, which of course is 3/2. And there's just a few more examples for you to have as a review for you, and hopefully that helps today.